So far, we have been studying zeros of single variable polynomials, and we proved many things. At the end, we got to Galois theory, and we realized how much symmetries of zeros of polynomial can give us information about all the zeros of the polynomial. After adding the zeros, we got the splitting fields and so on. So now the question is, can we find a field that contains all the zeros of every polynomial in f bracket x? So whenever we say all the zeros, we have to be slightly careful because we know that we might have different copies of the same splitting field. So here we mean essentially having one copy of a splitting field inside this larger field. Intuitively, what we can do, we can start with a polynomial, take its splitting field, take another polynomial, multiply it by the previous one, and take splitting field of this new polynomial. So that way, it does include splitting field of the previous polynomial. So, and we want to continue this process till we exhaust all the polynomials. If we had countably many polynomials, then we could actually do this process using induction. But unfortunately, the cardinality of the polynomials is not necessarily countable. So we need another tool from set theory to make this process formal. As we will learn in today's lecture, this can be done using axiom of choice. In fact, an equivalent form of axiom of choice, which is called Zorn's lemma, is particularly effective in algebra and many problems in algebra, as we will describe. But before we get ahead of ourselves, let's go back and define the basics of the field theory part of this discussion. What do we mean by having all the zeros? What kind of field is that? Remember, over Q or over real numbers, we have proved the fundamental theorem of algebra, which says that complex numbers, if I give you a polynomial with coefficients in complex numbers, then we can find all the zeros of this polynomial in the complex numbers themselves. So this brings us to the definition of algebraically closed fields. We say a field F is algebraically closed if every polynomial that I give you with coefficients, every non-constant polynomial that I give you with coefficients inside F has a zero inside F. If every non-constant polynomial with coefficients inside the field capital F has a zero inside capital F, then we say this field is algebraically closed. Okay, so now, as we have pointed out, complex numbers using the fundamental theorem of algebra is an algebraically closed field. I'm a bit sick. Okay, so now we want to see different forms of the same property. So, for instance, one way of saying that a field is algebraically closed is saying that every polynomial can be factored into linear, can be decomposed into linear factors in f bracket x. So it's it seems that it is more general than saying that it has only one single zero, but one can use induction on the degree of the polynomial and factor it one at a time, factor out linear factors one at a time, and get complete factorization into linear factors, complete decomposition into linear factors. So every non-constant polynomial can be factored, can be decomposed into linear factors in f bracket x. So this statement is equivalent to saying that the field F is algebraically closed, which means every non-constant polynomial has 1 0 inside f bracket F, inside F. It has at least 1 0 inside F. Now, these are statements within F. Now we can translate it and say something about the algebraic extensions of F. So far, we are saying that anything inside can be factored into linear, can be decomposed into linear factors. Now we want to say that there is no non-trivial algebraic extension. So this is equivalent to saying that if E over F is an algebraic extension of the field F, then it is the field F. We don't have any non-trivial extension of the field F that is algebraic. Okay, so let's go through the proof. Let's go from 1 to 2. 1 to 2 is actually immediate, because if I can decompose a polynomial into linear factors, each one of the linear factors would contribute a 0. So in particular, if I evaluate both sides at alpha 1, I get a 0 of F, and then therefore alpha 1 would be a 0 of F, which is inside capital F. This is true for every non-constant polynomial F, and therefore the field capital F is algebraically closed. Now, let's assume that the field is algebraically closed and try to show that every algebraic extension is F. There is no non-trivial algebraic extension. So let's start with an algebraic extension E, and let's pick an element alpha inside E, and I want to show that alpha belongs to F. So I'm going to look at the minimal polynomial of alpha. I need to show that it is of degree 1. As soon as I show it is of degree 1, that implies that alpha is indeed inside F. So I'm going to look at the minimal polynomial of alpha. We do know that this is an irreducible polynomial of F bracket X. But on the other hand, by our assumption, because capital F is algebraically closed, every non-constant polynomial has a 0 inside F. So this minimal polynomial of alpha has a 0, let's call it alpha prime, inside F. Now I can use factor theorem. So by factor theorem, this minimal polynomial has a factor of the form x minus alpha prime. But this minimal polynomial is supposed to be irreducible. So this means that it does not have a non-trivial factorization. That would imply that the minimal polynomial is itself x minus alpha prime. Okay, so because it is irreducible, it cannot be factored into the product of lower degree polynomials. Because of this factorization that we have over here, we can deduce that degree of the minimal polynomial should be 1. The minimal polynomial should be precisely x minus alpha prime. Remember that both of them are monic polynomials, so we get the equality. And that means that alpha, which is a 0 of this polynomial, is alpha prime, and that belongs to the field capital F. That finishes the proof of this step. Now let's assume that every algebraic extension is F. There is no non-trivial algebraic extension. I want to show that every polynomial splits completely inside F. So how do we do it? We start with a non-constant polynomial. I'm going to consider a splitting field of this polynomial over the field capital F. That splitting field gives me an algebraic extension of the field capital F. But by our hypothesis, there is no non-trivial algebraic extension. So E is F, which means the polynomial small f splits over capital F. So that means there are elements alpha 1 dot alpha d inside this field capital F, so that we can write down the polynomial as its leading coefficient times these linear factors. And that's exactly what we wanted to show. So altogether, we got that these three properties are equivalent. My field is algebraically closed. That means that every non-constant polynomial has at least 1 0 inside F. Every non-constant polynomial can be decomposed into linear factors, and there is no non-trivial algebraic extension. Okay, so now we get to the main theorem that we want to prove in today's lecture and the next lecture. So What is it? It says that every field that I give you, there is an algebraic extension that I'm going to denote by f bar. So f bar over f is an algebraic extension. And at the same time, f bar is algebraically closed. So this is the existence part. And we will also show the uniqueness part of this. And we will show that such an algebraic extension, which is algebraically closed, is unique up to isomorphism. We call it an algebraic closure of F. So any two algebraic closures of F are isomorphic. So we will prove existence and uniqueness separately. Okay, so as I've described at the beginning of lecture, the proof will be a systematic way of gluing together all the splitting fields that we can get through polynomials, splitting fields of polynomials in F bracket X. Whenever you are doing a process infinitely many times, you need some result from set theory to legitimize your process. And the result that we are going to use, I mean, the statement that we are going to use from set theory is related to axiom of choice. So what is this axiom of choice? So axiom of choice says that if I give you a family of non-empty sets, so let's call them x sub I, and capital I is just an index set. It's a non-empty set, and I is varying, small I is varying inside this index set. And x sub I is a family of non-empty sets. Now, what axiom of choice says is that you can always choose elements from non-empty sets, even if there are infinitely many of them. Now, to make it precise, it means that you can find a function, there is a function from the index set to the union of these sets, so that for the index I, f of I gives me an element from this non-empty set x sub I. So there exists a function so that f of I belongs to x sub I. This is axiom of choice. I mean, as you can see, this is quite intuitive. It seems that it should be true, of course, and that's why it is part of the axioms of set theory. But it has many equivalent forms that are not so intuitive anymore. Okay, so one of those is called Zorn's lemma. In order to formulate Zorn's lemma, I need to define partially ordered sets. What is an upper bound of a subset of a partially ordered set? What is a chain of inside a partially ordered set? And what is a maximal element of a partially ordered set? So after we define these concepts, we can formulate Zorn's lemma. Okay, let's start with what a partially ordered set is. A set, let's call it sigma, is called a partially ordered set if we have a relation between the elements of them that's kind of like comparing. So we have this kind of relation, and this relation is supposed to be like an inequality. So every A should be at most itself. If A is at most B and B is at most A, then they should be equal. If A is at most B and B is at most C, then A should be at most C. So if I give you a set sigma with such an ordering, then we say it's a partially ordered set. And we abbreviate it and say it's a poset, partially ordered set. So we abbreviate it and we say it's a poset. A typical example of a poset is the power set of a non-empty set. So if I give you a non-empty set and consider all the subsets of this, then with inclusion, this power set, we call it the power set of X with inclusion forms a poset because if I give you two subsets, I can ask myself whether or not A is a subset of B or not. And if A is a subset of B and B is a subset of A, of course A and B are equal. If A is a subset of B and B is a subset of C, then A is a subset of C, and everything is a subset of itself. So power sets and inclusion form a poset. Another source of getting posets is starting with some poset and taking a subset of that. So I can start with any poset that you give me and then just consider a non-empty subset of that poset. So again, with the same ordering as the original poset, I get a new poset. So you see the key point here is that I cannot necessarily compare every two elements. So like subsets of a given set, those two subsets of a given set, they are not necessarily, one of them is not necessarily contained inside the other one. You cannot necessarily compare them. That's why it's called partially ordered set. Okay, so now we have two main examples. You can start with a power set and take any subset of that and then take inclusion. So that way you get a lot of posets. Now, what is a chain or totally ordered set? So C is called a chain or totally ordered set if it is a poset and every two elements can be compared. So if C is a poset, and for every A and B inside this chain, either A is at most B or B is at most A, then we call it either totally ordered or chain. So why do we call it chain? Because an important example can come up from this. Let's say I give you a bunch of subsets of another set X, so that A1 is included inside A2 and so on. So I'm giving you a chain of sets. Each one is contained in the next one. So then they form a chain in this set, in a sense of posets, a totally ordered set with respect to inclusion, because every two of them that I give you, I can compare. Okay, now we understand what is a poset, what is chain. Let's see what is an upper bound of a subset of a poset. So sigma and this less than or equal, curly less than or equal. Suppose that it's a poset. I give you a non-empty subset of this poset, then an element u of sigma is called an upper bound for this set A, an upper bound of this set A, if for every element A, small a inside this set, this small a is at most u. So I mean u is an upper bound for all the elements. But what is important is that u itself does not necessarily belong to the set capital A. So this upper bound doesn't have to be inside the set capital A. It can be outside, inside this partially ordered set that we started with. Now, if I give you, when I give you a partially ordered set, an element is called a maximal element if there is nothing on top of that. So what does that mean? This means if for some element inside this poset, that element happened to be at least m, then they should be equal. So there is nothing on top of m. If there is nothing on top of m, we call it a maximal element. Notice that we are not saying this small element m, small m is a maximum element. Maximum means that it is an upper bound for the set sigma. Every other element is at most m. But here we are not saying that. We are saying there is nothing on top of this. It has some similarity with maximal ideals. In fact, if I give you a unital ring and I let sigma be the set of all proper ideals of the ring capital A, then sigma in inclusion forms a poset, and a maximal element of this poset is precisely maximal ideals, the set of maximal ideals. Because an element inside sigma is maximal if there is nothing on top of this. This means when I give you an ideal that contains this ideal, it should be the entire ring, or the ideal that I've given you. That's the definition of maximal ideals. Another example, and non-example, is the following, that if I give you all the bounded subsets of, let's say, real line that are bounded from 0 to n, then this is a chain. Every two of these intervals I can compare. One of them is definitely contained in the next one, but nevertheless, it has no maximal element. Because if I pick any of these intervals, there is something on top of this. I can take n plus 1, and that would be larger. So this is a chain with no maximal element. So existence of a maximal element itself is an important issue. It's not clear under what condition a poset has a maximal element. Now, what Zorn's lemma tells us is that under what conditions, so it gives us a very good criterion to understand whether or not a poset has a maximal element. Okay, so what is the statement? Suppose that I start with a poset, a non-empty poset. If I tell you that every chain in sigma has an upper bound, so for every chain that you give me, I can find something inside sigma that is at least the elements inside this chain, then sigma has a maximal element. Intuitively, it's like this, that I start with an element inside sigma. If it's not maximal, I can find something on top of this. If that guy is not maximal, I can find something on top of this. And I continue like that. Then I get a chain. It has an upper bound. I take that upper bound and I continue like that, and so on. But this is not an ordinary induction anymore, because this process does not stop incountably many steps. And whenever you have this kind of infra-induction, that means that the axiom of choice is involved. Anyway, so what Zorn showed is that Zorn's lemma is equivalent to axiom of choice. So we are not going to go into the proof of this statement, why axiom of choice is equivalent to Zorn's lemma, but what we will do is we will use Zorn's lemma in different places in algebra. Zorn's lemma is a powerful tool that is often used in algebra. And intuitively, the reason that it is useful, I mean, I will explain it more within the proof of the next statement. The reason that Zorn's lemma is extremely useful in algebra is because algebraic structures or algebraic operations are the so-called local operations. They are involved, only finitely many values are involved in an operation. So that means that whenever I give you a chain and I want to look at the chain and find an upper bound for the chain, we often take the union of this chain and then ask ourselves whether or not this union has the same algebraic properties. Now, to check if it has the same algebraic properties, we have to work with certain algebraic operations. That means we need to work with finitely many values inside this union of elements inside the chain. Because there are finitely many values involved, and this is a chain, all these finitely many values belong to a single element inside the chain. Assuming that the elements of the chain satisfy this algebraic property, that means that these elements satisfy this relation between the operations that we are working with, and we get the desired result. This is a general kind of a scheme, and I'm trying to just motivate you, or giving you the general picture of why Zorn's lemma is often useful in algebraic statements. But let's make a concrete example out of this general scheme. So the next theorem, we will be using the next theorem later on in the course as well. It's also a very good example on how Zorn's lemma can be used in algebraic settings. Suppose A is a unital ring, and I give you a proper ideal of this A. For instance, you can even consider ideal 0. Then there is a maximal ideal that contains I naught. So there exists this M, which is a maximal ideal of A, and it contains I naught. Starting with any proper ideal, you can extend it and reach to a maximal ideal of the ring capital A. Okay, let's see how we can prove this statement. Let's start with defining a poset. So what is the poset? I consider all the ideals of A that contain I naught, but they are proper. First thing that we have to notice is that this set is non-empty. So often when we want to use Zorn's lemma, that's the first thing that we need to check. We have to make sure that the poset that we are working with is a non-empty poset. Why is that non-empty? Because I naught belongs to this set. I naught is a proper ideal, so it's not equal to the entire ring, and it does contain I naught. So I naught does belong to this poset, and therefore it's a non-empty set. So far so good. Now I want to show that sigma with inclusion has a maximal element. But why is that relevant to the thing that we want to understand? We want to show that there is a maximal ideal of A that contains I naught. So let's prove that a maximal element of the poset sigma is a maximal ideal of A, and it does contain I naught. So let's see why this is the case. So suppose M is a maximal element of sigma. Now we want to show that it is an ideal. It does contain I naught, and it is maximal. Okay, let's see why this is the case. Because it is inside sigma, it is an ideal, so that's so far so good. It does contain I naught, that's good. It is proper, so far so good. So M is a proper ideal, and it does contain I naught. So now it remains to check why M is maximal. Now suppose J is an ideal, is a proper ideal of A, which contains M. I want to show J is M, so that means it is maximal, M is maximal. But what do I know about M? I know M is maximal among elements of sigma. So if I know J belongs to sigma, we are done. But is that the case? Because M contains I naught, and M is a subset of J, we can deduce that I naught is also a subset of J. And J is a proper ideal of A. That means J does belong to sigma. Now I can use maximality of M inside sigma and observe that M is maximal inside sigma. It is contained inside J, and J is inside sigma. Altogether, we conclude J is equal to M. That means M is a maximal ideal of A. Okay, so far so good. That means that it's enough to show sigma has a maximal element. So I'm going to use Zorn's lemma to show sigma has maximal element. By Zorn's lemma to show sigma has maximal element, it's enough to show that every chain has an upper bound. This is the place, again, let me emphasize, this is exactly the place why Zorn's lemma is so effective in algebra. So this is the part that I've explained it earlier, but let me go through it again in this general format and explain why this kind of scheme is quite useful in algebra. Suppose I give you a chain consisting of certain algebraic objects. So here, for instance, in this example, we are working with proper ideals or ideals of A. Okay, so being an ideal is something algebraic. Now we look at the union of these. And my claim is that their union of elements inside a chain is going to satisfy the same algebraic properties, meaning in this case it will be an ideal again. So union of a chain of ideals is again an ideal. So that's an example that you can have in mind, but any algebraic object can be of this form. Algebraic objects are defined in terms of certain operations, like ideals are defined using addition and multiplication. So in order to check if the union has the same algebraic operation, we have to take these finitely many elements from this union. Because these operations involve only finitely many elements, I need to take finitely many elements from this union and check whether or not they satisfy the same properties with respect to the operations that we have. But because these are chains, when I give you finitely many elements inside these chains, there is a largest one. And all these elements belong to the largest one. So that means, then I have to check whether or not as these equations are satisfied in a single element I of this chain. But that is the case because every element of this chain does satisfy the desired algebraic operations. So that's why the union should also satisfy it. You see, this is a quite general scheme that if I give you a chain of algebraic objects, their union should be again an algebraic object with the same properties. Now, we will see many instances of the same phenomena, like union of ideals, union of chain of ideals, union of chain of fields, union of chain of subfields, union of chain of subrings, and so on. But in this example, let's go over the example when I's are ideals. And we want to say that the union of chain of ideals is again an ideal of A. So that means I'm going to pick two elements from this ideal, and I need to show that there's the summation is inside J again. And then I have to pick some element inside the ring A and show that A times X is also inside the union. So let's start with X and X prime being inside J. That means there are two elements of the chain, I and I prime, where X belongs to one of them and X prime belongs to the next one. Because C is a chain, we can compare these sets. So either I is a subset of I prime or I prime is a subset of I. So without utter generality, I can assume that, let's say, I is a subset of I prime. And that means both X and X prime belong to I prime. Now, I prime is an ideal of A. That means for every element small a that you give me, A times X plus X prime belongs to I prime. And therefore, AX plus X prime belongs to the union of these ideals. I prime is one of those ideals, so it does belong to J, because I prime is a subset of J. So altogether, we are deducing that J is indeed an ideal of A. That shows the first step. Now, in order to show that it is an upper bound, so we are taking the union, of course, it's going to contain all of them, so that's good. But why does it belong to sigma? Sigma consists of elements, okay, where is sigma? Sigma consists of elements that are ideal. So far, so good. Now, next, I need to check why I not belongs to this and why it is proper. So this part is easy. Let's go to why it is proper. Okay, so suppose it's not proper, then 1 belongs to this ideal. This means 1 should belong to the union of these ideals. That means for some ideal inside this chain, 1 belongs to this ideal. But when 1 belongs to an ideal, it is the entire ring. That's a contradiction, because every element inside this chain is supposed to be a proper ideal. So that's a contradiction. As sigma, and including C and sigma, all of them consist of proper ideals. So that gives me a contradiction. Therefore, it is indeed a proper ideal. Okay, so now I need to check why I naught belongs, why I naught is a subset of J, but that's rather easy because C is a non-empty chain. That means for every, you pick your favorite element inside this chain, then I would be a subset of J, but I is also inside sigma, so I naught is a subset of I. Altogether that we get I naught is a subset of J. So J is indeed an element of sigma. And clearly, it is an upper bound for the chain because every element of the chain is a subset of J, and it is inside sigma. So we get that every chain inside sigma has an upper bound, and therefore, by Zorn's lemma, sigma has a maximal element, and that finishes the proof. Okay, so we've seen an important example on how to use Zorn's lemma. And we saw that any maximal ideal contains any proper ideal is contained in some maximal ideal. Okay, so next I'm going to give you a scheme of how to show existence of an algebraic closure of a field F. Let's start with what it means. It means that whatever polynomial I give you, small f, non-constant polynomial, I should be able to find some element alpha sub f inside this algebraic closure, which is a 0 of this polynomial. Okay, so I need to find a 0 for each one. Now, let's go back to Kronecker's theorem. How did we do it for a single polynomial, let alone all the polynomials at the same time? So just one polynomial at a time. For one polynomial at a time, what we did was we started with ring of polynomials with coefficients inside capital F, and we modded out by the ideal generated by F, at least when F is an irreducible polynomial. This is what we did. So we started with an irreducible polynomial, and then we mod out F bracket X by the ideal generated by F. In that case, we showed the coset that's represented by X is a 0 of F in the quotient ring. Now we want to follow the same principle. But let's also point out how this irreducibility came to the picture. Irreducibility came to the picture because when it is irreducible, the ideal generated by F is a maximal ideal, and therefore the factor, the quotient ring, is a field. So that's why irreducibility was important, because of maximal ideal. Now we want to do the same principle for all the polynomials at the same time. But this time, so last time it was one variable for one polynomial, and the 0 was represented by X. Now we have a lot of zeros, so we need a lot of variables. So for every polynomial, small f, non-constant polynomial, I'm going to assign a variable x sub f, and I'm going to consider this huge ring, the ring with a lot of variables, a ring of polynomials with a lot of variables, one variable assigned to every polynomial. So this is still a ring of polynomials with a lot of variables, infinitely many variables, and what we are going to do is we are going to find a quotient of A that's going to be a field, and this field is going to contain zeros, at least 1 0 for every polynomial. So remember, A over M is a field if and only if M is a maximal ideal. So this means we need to look for a maximal ideal inside A. Okay, what kind of maximal? So we want to make sure that when we mod out, then these polynomials have zeros. But what zero? Again, going through the model that we have over here, the zero here was represented by x. So here we want to get this alpha sub f to be represented by x sub f plus m. Again, following this one variable, one polynomial at a time, we want to set alpha sub f to be the coset represented by x sub f, and we want this guy to be a zero of the polynomial f. But what does that mean? When I evaluate f at alpha f, I get that it is the coset. So when I evaluate it at alpha f, this is like evaluating it at x sub f and then looking at the coset that's represented by f of x sub f. So saying that this is supposed to be a zero of f, this is equivalent to saying that f of x sub f belongs to the maximal ideal that we don't know what it is, to the maximal ideal M, because this is supposed to be zero. So that would imply that f of x sub f should belong to M for every f, for every non-constant polynomial f. So altogether, what do we end up getting? We are saying that the ideal generated by these guys, so there are infinitely many of them, but whatever it is, the ideal, the smallest ideal that contains all of these elements, let's call it I naught, we need to find a maximal ideal that contains this I naught. Okay, so we need to find a maximal ideal. We need to find a maximal ideal that contains all these f of x sub f's. Again, so we want to find an ideal here in the ring of polynomials with this many variables, so that I naught, which is the ideal generated by f of x sub f's, is a subset of M, and A over M is a field. Again, A over M is a field if and only if M is a maximal ideal. So we are looking for a maximal ideal that contains I naught. By the previous theorem that we proved, whenever I give you a proper ideal I naught, then it is contained in some maximal ideal. So we do get existence of this M as soon as we show I naught is a proper ideal. So as soon as we show I naught is a proper ideal, we can deduce existence of a maximal ideal M that contains I naught. Let's see why I naught is proper. Suppose to the contrary that it is not proper. That means 1 belongs to this ideal. What does that mean? I naught is an ideal generated by these elements. This means every element inside I naught is a linear composition, a linear combination of these elements. So I can find elements a sub I inside the ring, this huge ring, and write down 1 as a 1 times f of f1 of f1 of x, f1, f2 of f, x, f2, and fn of x, fn. I can find some fi's inside this ring of binomials and then write down 1 as an alinear combination of fi x of fi. So there are too many indices, there are too many decorations. In order to make it a bit more simple, we notice a few things. These a sub i's are multivariable polynomials, but every polynomial only involves finitely many variables. So even though I've started with a huge number of variables over here, one variable for every non-constant polynomial, but every element of this ring has only finitely many variables. So let's say these variables, let's call them the variables that are involved inside a sub I. Suppose that they are only x1 dot xn. And let's also label these variables instead of x sub f1, x sub f2, and so on. Let's simply label them by x1 dot xn. So I start with labeling these guys x1 dot xn. And if I need more variables for a sub i's, I am going to call them x sub n plus 1, x sub n plus 2, and so on, till I get these finitely many variables. And for sure, I can assume that a sub i's belong to this ring of polynomials that have finitely many variables. And this equation over here can be rewritten as this, that 1 is a1 that depends on these variables, f1 of x1 only depending on the first variable x1, and then similarly till we get to a sub n, a polynomial in terms of x1 dot xm times a polynomial that just only depends on x sub n. You want to say that this star cannot hold. We cannot have such an equation. And the magic is evaluating both sides at some value. You see, if this equation is true, then it is true after evaluating both sides at everything that we want. In particular, I can plug in a 0 of f1 for x1, a 0 of f2 for x2, and a 0 of fn for xn. So that way, the right-hand side will be 0, because each one of these terms will be 0. But the left-hand side is always 1, and that way we get a contradiction. But where can I find zeros for f sub i's? That's easy. We take a splitting field of the product of these polynomials. So let E be a splitting field of the product of these polynomials over the base field capital F. In this splitting field, I can find zeros for f sub i's. Now, the rest of the variables are not quite important for us. So let's say I put zeros for the rest of the variables. What do I mean by the rest of the variables? So here we might have more variables for a sub i's, only n variables. Here, this is n. So only n variables are coming from these polynomials, but the rest, we don't have any restriction, so we can put them whatever value we want. Let's set them zeros. After evaluating this equality at alpha 1 dot alpha n, the left-hand side will be 1, but the right-hand side will be 0, and we get a contradiction. So that means that this ideal I0 is indeed a proper ideal, and so by the theorem that we proved, there is a field. There is a maximal ideal that contains I0. That means this maximal ideal contains f of x sub f's for every non-constant polynomial. Now, if I let L to be the factor, the quotient ring A over M, and let alpha M to be the coset represented by x sub f inside L, then as before, f of alpha M is f of x sub f plus M, and that is 0. And that means that because this is inside f, this is 0, and that means that we end up finding a field extension so that for every non-constant polynomial has a 0 inside L. Now, an immediate corollary is that there is an algebraic extension of f where all the non-zero polynomials have zeros. Why is that? Because I take the algebraic closure of f inside L in the previous lemma. So altogether, we get this corollary that if f is a field, there is an algebraic field extension k over f, so that every non-constant polynomial has a 0 inside k. Let's finish proof of this corollary, and then I stop to make this session a bit shorter for you guys to be able to catch up. And then we continue the proof of existence and uniqueness of algebraic closures in the next videos. But let's finish the proof of this corollary. By the previous lemma, we deduce that there is a field extension L over f such that every non-constant polynomial has a 0 inside L. Now we let k be the algebraic closure of the base field over inside this larger field L. And notice that, we have proved that when I take all the elements of L that are algebraic over F, they form a field, and we call it the algebraic closure. In particular, for every non-constant polynomial f, alpha sub f that we chose, alpha sub f is algebraic because it's a 0 of the polynomial, is a 0 of the non-constant polynomial, and therefore it's algebraic, and so it belongs to k. So altogether, we get that k over f is an algebraic extension, and it does contain a 0 of every non-constant polynomial in f bracket x. We will continue. So the proof after this is actually fairly short, the proof of existence, but let's continue in the next video for now.